Hi, my name is Nicholas Wiley, and this is Material and Energy Balance, Homework 2, Part 2. Now what we're going to be doing is we're going to start from the generic cubic equation of state, and then we're going to derive a cubic polynomial expression for the compressibility factor. This is our generic cubic equation of state right here, and this is going to be our compressibility factor formula. Now the first step we are going to do is we're going to make this z because it equals PV over RT, so we have to multiply everything else by that. Very simple to start. Also, quick comment, I drew this real quick before the video. I wanted to explain why we were doing this. By making a cubic compressibility factor, when we find the roots, we'll be able to find each point along here so that we can take the area. I believe that it's inverse, so it would be more like that. But so that these two areas are equal on both sides of this point right here. I believe that this is the liquid and this is the vapor point, and then this is some imaginary point in the middle. But we want to get these areas to be equal so that we can find the actual vapor pressure along this whole thing, as this line is the equilibrium part. So what we're going to do is, as shown before, we're trying to get z, and below here we're going to divide by v, and we're going to do the same thing down here, and we are left with all this, right? Just simple algebra rearranging. Now, as you can see here, simply after changing these to ones simplify after changing these to 1 after dividing and multiplying. So, what we have here is you can see the AP RT squared, R squared, T squared, Z. Pretty much what we did was we moved this VRT up here, and then we changed that V according to this to the RTZ. So you can see that since it was down here, we changed that, so it was RT down here, and then we're going to multiply that by RTZ, and then since that's on the bottom, it would go to the top. We have the P. That's all I did. And then again, it was B over V, so RTZ, P on top, just flip that. That's what we did. Same for these in here, just rearranging. Now what we're going to do is we're going to use these beta and this Q value right here, and what we're going to do is we are going to change this right here. So the beta PRT, as you can see right here, we're just going to have beta over Z. And then the Q beta, I wrote out some steps right here. So we have this right here, and since beta is BP over RT, sorry, my roommates are being very loud. That's going to turn into a beta over B because it's PRT, and then the A is right there. So we're going to have alpha A beta over BRT after that, since we left these times 1 over Z, and then we're just going to end with Q beta over Z. I don't know if that was the best explanation, but I tried to write out the steps to make it a little bit more clear, since that part was the most difficult. And then again, just rearranging BP over RT, beta over Z, the Z is left over. Now the next step is what we're going to do is just multiply by 1 over Z, because we have a lot of things that we could simplify by doing this. So what we're going to end up with is we're going to end with 1 equals 1 over Z minus beta, minus Q beta over Z plus epsilon B, and then Z plus sigma beta. And then we're going to make a common denominator so that we end up with something that looks like this. And now what we're going to do is, following your example, Carlos, is I'm going to arrange it from Z cubed all the way to the constants. So what we have is Sorry, I just blanked for a second. So what we have, a lot of these signs are going to look flipped, but that's because we're going to be moving them to the other side of the equation. We're going to make this equal to 0. We're going to drive it to 0. We are going to use, it was sorry, let me just exit out. We're going to use, why we're doing that is we are going to use Cardano's formula, which is pretty much just finding the zeros of this function right here. And we're going to use those to find those 3 different points along that curve so we can make the areas equal. Also, I simplified this just like you, Carlos. So this is going to be implemented directly into our code, this right here. So use to find 3 roots for finding areas above and below the van der Waals loop, which the loop, again, is this, which is like these 2 areas right here, how it goes above and below. So that's not actually the true way it behaves, as this is just a prediction. So we're going to use something else to figure out what that actual vapor pressure is. Now, hopefully that was explained pretty clearly. That was me deriving a cubic polynomial expression for the compressibility factor using the generic cubic equation of state. Thank you.